Okay, so model selection. It's a very simple but useful application of validation. Okay, so remember in validation you have your data set dn and you have split it into your training set dn minus k and your validation set dk. So let's call this the training set dtrain and let's call this the validation set dval. Now, what is the problem in model selection? So imagine that you have models. Okay. Now, typically when we say models, you know, we mean different hypotheses sets. So that's the mode in which I will, you know, frame the discussion. But models can have the same hypothesis set but different algorithms. Okay. So there can be many different ways in which learning models can differ. Okay. So imagine that I have, you know, model 1, model 2, model 3, up to model big M. Model big M, okay? And typically this means that you've got hypothesis set 1, okay, linear models. And you've got hypothesis set 2, you know, neural networks. And you've got hypothesis set 3, you know, radial basis functions, and so on, support vector machines, and etc., etc. Okay, M. So you have, let's say, M different models. Okay, now what's the problem? So you have your data set dn, okay, your full data set, and if you train your model 1, you get G1. If you train your model 2, you get G2. If you train your model 3, you get G3, and so on, you get Gm. Okay, good. So the model selection problem is, well, you know, I've trained all my models, okay, and now I need to pick one. Which one should I pick? And, you know, what's its out of sample error? Okay, so I pick one. Let's say this guy wins. Okay, so I pick this guy, and I've got E in of G2. And what is E out of G2? So the first question is, you know, why did I pick G2? Okay, and how do I compute its out of sample error, you know, E out of G2? Okay, so, you know, one of the typical applications of this is to think of the supervisor who doesn't know what the heck is going on in the models. So you can think of the models as being black boxes behind closed doors. So the supervisor has M minions and gives the machine learning problem, i.e. the data set, to the M minions and says go. And the M minions produce, you know, final hypotheses. Okay, now, you know, on what basis should you even pick one of these final hypotheses? Because imagine if this guy was trained with linear models and this guy was trained with the most complicated this and that neural networks. And this guy, you know, got an in-sample error of, you know, close to 0, but you have no idea, because it's behind closed doors, you have no idea what's its out-of-sample error. Okay? And you have no idea or what you think its out of sample error is, and same here. So you need to pick one. Okay? And validation can be an answer to this problem. Okay? So let me show you how we solve this problem in the validation setting. Okay? So, you know, we now don't give my minions the full data set. We give my minions the training data set. So it's very simple. You have your models, M1, M2, M3, and so on, up to M sub M. Okay. You give the training data set to your minions, to your different models, and they each produce a deficient hypothesis. That's the beauty of what's going on, to realize that, well, they're actually producing deficient hypotheses. G1 prime, G1 deficient, G2 deficient, G3 deficient, and so on, GM deficient. Okay, and now what you can do, okay, is because you had the foresight to save a validation set which they never got to see, you can now run you can think of these as finalists, okay, in a competition. So each of these guys, each state has produced a finalist. Each minion has produced their final hypothesis, and you can think of these as entering into the final competition. So these are the finalists. Okay, and now we have a training data set that produced these finalists, and now we have this validation data set which we can run these finalists through. Okay? And they will each produce a validation error. Let me call this guy's validation error E1, let me call this guy's validation error E2, and E3, and so on. EM. Okay. Now let me remind you, what are these validation errors estimating? These validation errors are estimating the out-of-sample error for the deficient hypotheses. So E1 is approximately equal to E out of G1 minus, let us assume, okay? And E2, and you can go and sit down and do all the analysis. E2 is approximately equal to E out of G2 minus, okay, and so on. Approximately equal to E out of G3 minus, and this is approximately equal to E out of Gm minus. Okay, and now simple solution to the model selection problem. Pick the model which got the smallest validation error. So you can think of this as a new hypothesis set. These G minuses are new hypothesis, is a new hypothesis set. So let me define a deficient hypothesis set H minus, which is just the finite collection of hypotheses. G1 minus, G2 minus, G3 minus, and so on, up to Gm minus. Okay, it's a finite collection of hypotheses, finite. Okay, and now I'm going to evaluate this deficient hypothesis set, okay, of finalists on the data set which I'm calling my validation data set. So I pick one based on dval. And that's effectively what I'm doing. Okay, so I reduce my models to their finalists, and then I use my validation set to pick one of the finalists. Okay, and what do I get from this? I get that, when I pick one. Okay, so now, even though each validation error independently approximates the corresponding out of sample error, that's no longer the case after I pick. I have to pay a price for picking on the basis of the validation data. So what I will find is that when I pick the best one, let's call it G minus star. So this gives me G minus star, my final deficient hypothesis. Then E out of G minus star will be at most eval of G minus star. Now I'm going to have to apply not the single hypothesis Hafting bound, but I'm going to have to apply the M hypothesis Hafting bound, plus order of the square root of log M over K. Okay, why log M? Because that's the size of this hypothesis set finite, and why K? Because that's the size of my validation set which I left out. And we typically pick K approximately N over 5. So you'll give your minions 80% of the data to chug along. And the nice thing here is you don't need to know what they did. Okay, they just produce the finalists, and you treat the finalists as a new hypothesis set, and you pick one from here on the basis of eval. Okay, and surprise, surprise. Let's say you pick this guy, you are making a leap of faith. Okay, what's the leap of faith? You're making a leap of faith that the model which had the best deficient hypothesis, okay, will also produce the best final hypothesis, because just as we talked about restoring the data set, you don't output G star minus. You don't output G star minus, because it's always going to be the case that G star minus, it's always going to be the case that G star trained on all data will be better than G star minus. So you output from here G2. What does that mean? You run model 2 with all the data. So you take model 2, you run all the data, Dn, and can compute G2. Okay. Now, there's a leap of faith here. What's the leap of faith? That's actually a leap of faith. It need not be necessarily the case. So this is perfectly valid, and you have with high probability, picked the hypothesis that the deficient hypothesis that's big, that's best if K is reasonably large enough. Okay, and it is also the case that G2 will be better than G2 minus, or G star will be better than G star minus. That's also the case. What is the leap of faith is that it's not necessarily the case that the model with the best deficient hypothesis is the model that will produce the best full hypothesis. Because think about what these deficient hypotheses are. These deficient hypotheses are all trained on the deficient data. It's possible that, you know, the deficient data set, the training set, is right on the cusp of when this model will become spectacular. Okay? And if you had given it that extra k data points, this model would be spectacular, and G3 might be the best. Okay? It's just that when you took those extra k data points away, that really slammed this model. So this model happens to be very sensitive to those k data points. In other words, G minus for this model can be very different to G for this model. On the other hand, this model may be very robust. You can take away lots of data points and it's, you know, not going to suffer too much. So G minus and G are close. Okay, but G minus for this guy, when you take away the deficient, when you take away the k validation points and train on the deficient data, this guy's G minus is much better than this guy's G minus. Whereas if you gave all the data here, this guy would be the clear winner. Okay, so that's a leap of faith, which happens very often in practice. Okay, that, you know, when you take away a certain fixed amount of data from all the models, they all sort of drop in performance comparably. It's possible that some models drop a lot more than others, in which case you may end up picking the wrong model. But at least we have a principled approach for model selection. Okay. Okay. And now let me show you how we can use this to pick the regularization parameter, which from the last lecture we saw is an important parameter to pick, because it is what we have, it's the knob we have to control how much we sort of break the learning algorithm and prevent it from fitting the noise. Okay? And it's an important parameter to pick. Okay? And so, you know, picking lambda. Okay, so picking the regularization parameter lambda, very easy. I don't even need to say much. What's going to be going on? I define models for different lambda. That's it. So my models will all be defined with the same hypothesis set. So they'll all have, you know, each of my models will have the same hypothesis set. So whatever it happens to be, let's say linear models for linear regression. So same hypothesis set H. Okay, same hypothesis set H, and that's perfectly valid. So models can have the same hypothesis set H, but different amounts of regularization. So, you know, you could define a set of regularization parameters starting from, let's say, 0.0001 and then going up in, let's say, multiples of 2. So 0.0002 all the way up to, you know, and then 0.0004 and so on, you know, going up, let's say, to 10. Okay, and that's not going to be too many. Okay, so if I divide, so that's not going to be too many models, so that the error bar for the validation error will be reasonable. And, you know, I can define this as lambda 1, lambda 2, lambda 3, and so on up to lambda m. And I define one model with lambda 1, another model with lambda 2, another model with lambda 3, and so on, lambda m. And I have defined m models, and then I just run model selection. So I train the models with each of their respective regularization parameters, then I validate them on the validation data. Okay, I get the validation errors, pick the model that gave me the best validation. Okay, and now, you know, it's an interesting question whether I should run the model on all the data with to produce the final hypothesis. Okay, and you know, you can do that, and there are slightly more sophisticated things you can do, because now that you have more data, usually you'll need slightly less regularization. So you may be able to correct a little bit for the fact that you have more data. You need to break less to get the optimal hypothesis from whatever that model is, whatever that lambda is. Okay, so, you know, there's a lot of interesting things, you know, to think about when it comes to model selection to pick the right lambda and model selection in general. But now you have the big picture of how we do model selection using a validation set. Okay, and let's go back to now validation and discuss an issue that might have been bugging you. So we're done with model selection. Let's go back to validation. Okay, and discuss the general philosophy. So you're going to output G, okay, and G has E out of G. Okay, and basically what we said was, you know, E out of G is approximately equal to E out of G minus. So if you're using validation, okay, so you can get the deficient hypothesis, and, you know, E out of G is approximately E out of G minus, and then E out of G minus is approximately equal to E val, okay, of, you know, G minus. So E val is evaluated for G minus on the validation set. Okay? And then we just miraculously or just optimistically use that eval for E out. Okay? So this is a chain of equalities, and let's see what it depends on. Okay? So how close is E out of G to E out of G minus? These two will be close when G is approximately equal to G minus, which means that you want K to be as small as possible. So you want this deficient hypothesis to be trained on almost all the data. So you want K to be small so that N minus K is approximately equal to N. Okay, so you want K small for this to hold. Okay, but if K is small, then your validation set is a small number of data points. Okay? And so the error bar on this validation error will be large, order of 1 over root k. So the error bar here will be large. So to get this equality, tight, we would like to choose k large. Okay, k large. And that's because, the error bar on eval being close to E out of G minus, the error bar is order of 1 over root k. Okay? And so there seems to be a big trade-off here. Okay. I'm trying to estimate E out, and I'm stuck between a rock and a hard place. If I choose K small, I get this equality, but then validation error is useless. If I choose K large, then I don't get this equality, and so this is good. E out of eval of G minus is close to E out of G minus, but who cares? I'm outputting E out, I'm outputting G, so I need E out of G, and this will be far apart because this is really deficient if K is large. Okay. So the next issue we're going to address is this issue of K. Can I have my cake and eat it too? So is it possible for me to get away with K equal to 1? What about K equal to 1? Okay, that would be a miracle, right? Because if K equals 1, then these two are basically the same hypothesis. This is G, and this is deficient by 1 data point. Okay, but then if K equals 1, this is going to be wild, completely wild. Okay. So this is what we need to address if we're going to try to set K equals to 1. And so when we come back, I'll show you a method for having our cake and eating it, i.e. setting K equals to 1, and that's called cross-validation, the queen of validation techniques. Okay, so let's erase, come back, and talk about cross-validation. Bam, bam, bam.